Alright, so for this particular video, we're going to discuss another subtopic, another method of Laplace inverse, which is called as inversion using partial fraction. So remember, first we learn how to use inversion by using the table, and if it gets to a more complicated function, so we also have the choice of using the inversion of a shift theorem. But the inversion of a shift theorem doesn't always work because it can only work when you have the denominator consists of a function in the term of s plus a. Okay, and today we're going to discuss another method for which you're going to use it when your function is much more complicated, and it's called as the inversion using partial fraction. So the idea is going to be using partial fraction. Okay, and if you are already familiar with how to do partial fraction, so this is going to be a piece of cake for you, so there's going to be nothing new. But if you are not too familiar with the idea, then you're going to struggle a little bit on partial fraction. But in terms of Laplace inverse, it's not going to be that challenging, because after you have reduced that to a smaller fraction, automatically all you have to do is you can simply use the table and find the Laplace inverse of the function. Alright, so before we start with the examples first, let's revise a little bit on your partial fraction. So if you are already good at your partial fraction, so feel free to skip this. But if you have no idea or you need to brush up your skills on partial fraction, so please listen to this very carefully. So basically there are two types of function. So the first type of function is called as reducible function, and the second type is called as the irreducible function. So please make sure that you are familiar with this term, because I'll be saying this term over and over again, like the whole while that we're going to be discussing this particular topic. Alright, an example of reducible function is going to be this one. So I have a function of s squared plus 2s minus 3. And what does it mean by being reducible? Okay, being reducible means so the function can actually be reduced. So let me put over here. So function can be reduced. So what do I mean by reduced? So it means that it can actually be factorized. So that is going to be the easiest way to imagine that. So what happens is that you start with s to the power of 2, and you can actually factorize your function to factors with smaller power. Reduce to factors with smaller power. Alright, so here I have s to the power of 2. So when I say smaller power, meaning that this can actually be reduced to linear factor. So how do I actually know that this can actually be reduced to linear factor? So the idea is going to be very simple. So all you have to do is you have to use your calculator and find the roots of the expression. So remember what we did for underspin coefficient when we find the homogeneous solution? So that will be the same idea. So you're going to plug in, for this case, 1 equal a equal 1, b equal 2, c equal negative of 3, and then you find the roots. And if it's reducible, if it can be reduced, what happens is that you will get real number as the roots. So let me put over here, so real number as roots. Okay, so you will get a value of 1, value of 2, value of 3, and so on. For example, this case, so what happens is that you will get two values. So the first value is going to equal negative of 3, and the second value is going to equal 1. So therefore, right away we know that. So this can actually be reduced to two linear factors. So the first one is going to be s plus 3, because the roots is going to be negative 3, and the other one is going to be a linear factor of s minus 1. Okay, so if you can actually change your function to for example, this one is a quadratic expression, to two linear factors like this, you can actually factorize them. So that is called as a reducible function. And again, all you have to do is plug in the value of a, b, and c into your calculator and find what is going to be the value of the roots. And if the roots give you a real number, automatically, so the function can actually be reduced or factorized. Okay, so next, so let's have a look at the case of irreducible function. So a reducible function, of course, is going to be the opposite of that. So here we have an example of a function of s squared plus 2s plus 5. So what happens is that for this case, so the function cannot be factorized. Okay, so let me put a remark over here. So it cannot be reduced, or in another word, it cannot be factorized. So if it cannot be factorized, automatically there's nothing we can do about it. So we just have to leave it in this form. And what happens is that, how do you know that this cannot be factorized? So if you use your calculator for this, so this is my reducible function, you plug in a value of 1, a equal 1, b equal 2, and c equal 5 into your calculator. So you will have that the roots are going to come out as complex numbers. Remember in table 2, so we have seen how complex numbers looks like. So complex numbers are basically numbers that has real parts, which is going to be just a number 1, 2, 3, 4, 5, and so on. And it's also going to have another part which is called as the complex part with the I. And for this case, what happens is that when you plug in into your calculator, you will get two roots of negative 1 plus 2i and also negative 1 minus 2i. So we have seen this before in homogeneous in chapter 2, so this will be basically the same idea. So I always remind this to my students: if you're using the silver calculator or the white calculator with a white cover, the latest one, so good news for you, so you don't have to check for anything. But if you're using the gray calculator every single time, so please make sure that you check this calculator screen. If there is an R coming from the top right corner of your calculator, automatically this is going to be a complex number. So what is shown on the screen is the real part, and in order to find the complex part, you have to press shift equal. Okay, so you have to press shift equal, then only will give you the complex part. Okay, so what happened is that, so if your calculator give you complex number as the roots, automatically we know that the function cannot be reduced, it cannot be factorized. There is no other way. You have to leave it as it is. You cannot factorize this. The only way is to leave it like this, and this is called as an irreducible function. Okay, however, there are also special cases. So what do I mean by special cases? For example, you might come across something, a function that looks like this, so which is s cubed plus s squared plus s plus 1. So you can use your calculator to find the roots. So what happens is that your calculator will give you 3 roots. Of course, this is to the power of 3. Of course, your calculator will give you 3 roots. So the first root is going to be a number of negative 1. The second root is going to be I, and the third root is going to be negative I. So we know the fact that here, so this is negative 1, so this is a real number. But this two over here, 1 and negative 1, so this is actually a complex number. So if it's a complex number, meaning by, you cannot factorize them. Okay, so how do we reduce when we come across a function like this? Can it be reduced? Of course. So we have a real number right here, so of course it can actually be reduced. But how do we reduce that? Alright, so now using the fact that we have here, the first root is going to be negative 1, so we know that somehow this function, so we can end up with s, so it's minus 1, so it's going to be s plus 1. Okay, and of course there is going to be another factor over here, because this is s to the power of 1. Of course this is going to be a factor of s to the power of 2. But how do we know the preceding function? So we cannot tell for sure, because the other root is given in terms of complex number. But what we can do is that we can use long division and identify what kind of function is it going to be. So what I have to do is I'm going to divide s cubed plus s squared plus s plus 1, and this is going to be divided by s plus 1, so that I can figure out what is going to be the function. So the function right here. Okay, so all you have to do is when you do long division, only worry about the first term. So this is my first term, s cubed, and this is the first term of the division, which is going to be s. So I know that when I have s cubed divided by s, so that will come across as s to the power of 2. So therefore I'm going to have s to the power of 2 at the top. So multiply by both of the terms, I'm going to end up with x cubed plus s squared. And remember, this is always a minus operation, so this is gone and this is gone as well. So therefore I'm simply going to have s plus 1. I'm going to put down s plus 1. And again, when I have a look at the first term, so this is going to be s and this is s as well, and s divided by s, we know that that is simply going to be 1, so therefore I'm going to have a plus 1 right here. And when I multiplied, I'm going to end up with s plus 1, and this is also going to be gone. So therefore straight away I can write the fact that So this function over here is s cubed plus s squared plus s plus 1 is actually equivalent to s plus 1, so multiplied by s squared plus 1. So that is going to be my function. And of course, this is a linear factor, it's to the power of 1, and this over here is actually an irreducible function, so that is why it comes out as with these two complex roots, which are going to be 1 and also negative 1. Okay, so that is going to be like what you have to do when you come across cases like this, for which the roots give you combination of real number and also complex number. Okay, so now let's have a look at how do we make a complex fraction to a smaller fraction. So that is called as partial fraction decomposition, and that is a very important skill that you have to acquire in order to do Laplace inverse by using this. So it's called as partial fraction decomposition. It's called decomposition, decompose, because like you're going to change your complicated fraction to a smaller one that we can actually Laplace inverse. Let me pick a simple example. So let's say I have a function of s, let's put s at the top, and at the bottom I have two factors. So the function in the bracket, so those are called as being factors. So let's say that the first factor I have is a quadratic one. I have s squared plus s plus 2s plus 1, and the second one is I have a linear factor of s plus 2. Okay, so how do you decompose when you come across a fraction that looks like this? So this is a very complicated function. You cannot Laplace inverse this, so that is why you have to make it into smaller fraction that you can reduce and Laplace inverse. So that is the main reason why we do partial fraction. Okay, first of all, so you have to check the function. So what do I mean by check? So let me put a remark over here. So this one over here, this is non-linear. For functions that are non-linear, so you have to check if it's reducible. Check if it's reducible. Okay, and of course we can actually plug in the values into the calculator. A equal 1, B equal 2, and C equal 1, and you will get that this is going to be the case of equal roots, for which you will get that the roots are going to be negative of 1. So it's going to be negative 1 and also negative 1. Okay, so in your calculator, so the root will only come out once, so that is why. So this is going to be s over, so s squared plus 2s plus 1 is actually reducible, so it can be written as s plus 1 to the power of 2. Remember, so when your function is non-linear, so you have to check if it's reducible. If it can be reduced, reduce it, but only for non-linear. And for this one, we don't have to check for the second factor because this is already s to the power of 1. So we know that it's already linear. Then there's no need to do so, and just copy it as it is. So therefore, your function is going to be reduced to s over s plus 1 square, so multiplied by s plus 2. Okay, so now we have two linear factors. However, we're not done yet. So now we are going to start decomposing this. We're going to make it into smaller fractions. But before I show you the example, how do I change it into smaller fraction? So let me explain to you a couple of things that you have to know before we start doing that. Okay, so the first thing that you have to know about is the power inside. So let's have a look at this fraction over here. So this is a linear factor for which my s is given by to the power of 1. So this over here, the power on the inside, so I'm going to call this as the power on the inside. So the power of s inside the bracket is going to determine what goes on top. So let me write for you somewhere down here. So power of s inside the bracket, so determines what goes on top. So if you remember that for partial fraction, we're going to have a, b, c at the top. So how do we know whether it's going to be a or a multiplied by s? So that is going to be determined by the power of s inside the bracket. So let me put highlight over here, power of s inside the bracket. So it's going to determine what goes on top. Okay, and so what happened is that, so there's going to be another power that we're going to observe, so which is going to be referring to this one right here. So this is the power outside the bracket. So let me put a remark so you won't forget them. So power outside the bracket determines how many times so the factor come out. Okay, so the key point is that, so power outside the bracket, so it determines how many times the factor comes out. So there's got to be the two things that you have to observe every single time. Remember, the power inside determines what goes on top. So the power outside determines how many times the factor is going to come out. So let's talk about the first one first. So let's talk about this. So the power inside the bracket. So let me explain to you in detail what do I mean by the power of s inside the bracket, for example. So let's say if I have something like this. So I have something that is over s plus 1, and I know that I wanted to know what goes on top, like whether it should be only a at the top or it's got to be a multiplied by s at the top. So how do I know whether it's either going to be a or a multiplied by s? All I have to do is observe the power inside the bracket. So there's actually a bracket around, and this is actually to the power of 1, and this is going to be my s to the power of 1. And because inside here, so this is s to the power of 1, so what happened to the power on top? So how does this determine what goes on top? So let me put over here. So power of s on top is 1 power, so this is number 1 power lower than the bottom. Okay, and here I have s to the power of 1. Automatically at the top is going to be s to the power of 0, and then the s to the power of 0 is going to be multiplied by a constant. You can either use a, you can either use b or c, or whatever that you like to choose from a until z, as long as the power of s on top is going to be 1 power lower than the bottom. So here is going to be s to the power of 0, and of course I can actually simplify this, because we know that s to the power of 0 is simply going to be 1. So this is going to be a multiplied by 1, which is going to be a over s plus 1. So that is how we determine so what is going to go on top. If I were to give you more example, okay, let's say if I have something like this. So I have something that is going to be over s squared plus 1. Okay, so now what happened is that inside the bracket I have s to the power of 2, and I know that at the top must be 1 power lower. So meaning that at the top I'm going to have s to the power of 1, and also just not to s to the power of 1 by itself, and s to the power of 0. So now each of this are going to be multiplied by a constant. For example, I'm going to multiply this by a and multiply the back term by b. So therefore here I'm going to end up with as plus b, and that is going to be over s squared plus 1. Okay, so remember the bottom determines what goes on top. Well, let me show you another example. So let's see, now I have a cubic expression, so which is given by s cubed plus s squared plus 1. Again now, so the power at the bottom is given by s to the power of 3. Automatically at the top I know that I'm going to end up with s to the power of 2, s to the power of 1, and also s to the power of 0. Okay, so now I'm going to multiply this by a, multiply this by b, and multiply the last term by c. So therefore I'm going to end up with as squared plus bs plus c, and that is going to be over s cubed plus s squared plus 1. Okay, so that is how you determine what goes on top of your partial fraction. So whether it's going to be as square, or s cube, and so on, right? So the idea is going to apply for any power in your partial fraction. Okay, next, so let's try to decompose them now. So let's have a look at the example from the previous page, referring to the previous page. So from previous page, we have a function of s over s squared plus 2s plus 1 being multiplied by s plus 2. So like I mentioned to you before, first of all, so whatever that is not linear, so we have to try to reduce it first, and this can actually be reduced to s plus 1 to the power of 2. So our function has now become s over s plus 1 square, so multiplied by s plus 2. And now I'm going to reduce this to a smaller fraction, which is called as partial fraction. Okay, how do I know that how many fraction is this going to be? So I don't think there will be enough space. Let me put underneath. So how many fraction is this going to be reduced to? So it's going to depend on the power outside. Remember I mentioned just now? So the power outside here, this is the power of 2. So meaning by what happened? So this is this factor comes out twice. Okay, it's number of 2, so it's going to come out twice. So what happened when it come out twice? So the first is that it's going to come out over, so s plus 1 to the power of 1, and then the second time is going to be s plus 1 to the power of 2, and when it matches, you stopped, right? So this is to the power of 2, and this also to the power of 2, so that is the right time to stop. And for the second one, so this is for the second factor, so this is to the power of 1, so we know that it only come out once, one time only, so that is going to be over s plus 2 to the power of 1. Okay, so based on the power outside, we know that here, so we are going to end up with 3 partial fraction. Here goes 1, 2, and 3. So now we're going to determine what goes at the bottom. So if you have a look at the bottom of the partial fractions, so everywhere it is given by s to the power of 1 inside the bracket. So that is why. So here I'm going to end up with, this is going to be as to the power of 0, and this is going to be bs to the power of 0, and this also going to be cs to the power of 0. And of course, if I simplify, that is simply going to be a over s plus 1 plus b over s plus 1 square, and the last one is going to be c over s plus 2. So that will be the outcome. So this is how my partial fraction looks like. So it started with a very complicated fraction, which is referring to this one right here. I don't want to be in that form. I cannot Laplace inverse that, and I actually reduced that to a smaller fraction, which referring to this function right here, that I can actually Laplace inverse. That is the purpose. So that is what we want when we use partial fraction. Okay, let me show you one more example before we proceed to the real example. Okay, so for example, let's see if I have a function of s plus 2, and that is going to be over s plus 1, so multiplied by s squared plus 1 to the power of 2. Okay, first of all, how many fractions are we going to end up with? But before you start with that, identify first that the functions that are not linear, whether it's reducible or irreducible. So I'm referring to this one right here. So this one is already linear, no need to check. But s squared plus 1 is a quadratic expression. But if you use your calculator for this, you will find that the roots is going to be it's going to be I and negative I. So therefore, this is going to be irreducible. So there's no way that you can deal with that. Leave it as it is. So now when I observe like how many fractions am I going to have, like the power outside, this is to the power of 1. So that is to the power of 2. I know right away that I'm going to end up with 1 plus 2. So that is going to be 3 fractions. So the first fraction is going to be over s plus 1. So the second fraction is going to be over s squared plus 1 to the power of 1. And the third one is going to be s squared plus 1 to the power of 2. and I'm going to determine what goes on top for each of them. So based on the power inside the bracket, so this is s to the power of 1, okay, to the power of 1. This is to the power of 2, and this is also to the power of 2. So that is why. So here for the first one, I'm going to end up with a, because that is a multiplied by s to the power of 0. And then the middle fraction, so I have s to the power of 2, so I'm going to have s to the power of 1 and also s to the power of 0. So therefore here I'm going to have a constant of b and c. And the last one, again, I have 2, so therefore I'm going to have s to the power of 1 and also s to the power of 0. So here I'm going to have d and e. So therefore, if I simplify this, I'll end up with a over s plus 1 plus bs plus c over s squared plus 1 to the power of 1. And the last one is going to be ds plus e over s squared plus 1 to the power of 2. So that is going to be my partial fraction decomposition. So I hope you're familiar with this now, because I am going to start with the first example. Okay, however, before I start with the first example, so let me remind you about a very special case. Okay, special case. Let me put a remark right here. For example, let's say you come across something like this. So you have 2s plus 5 at the top, and that is going to be over s squared multiplied by s minus 1. Again, so I want you to bear in mind, so the fact that here, so we have s squared, but s squared is actually s plus 0 to the power of 2. And because of the to the power of 2 here, and this to the power of 1, so we know right away we're going to end up with 3 fractions. The first one is going to be over s plus 0 to the power of 1, and then I'm going to have s plus 0 to the power of 2, and then the last one is going to be over s minus 1, for which this is all to the power of 1. So I know that I will end up with a, b, and also c. Okay, however, so instead of writing the s square, so I'm referring to this one, so instead of like having them transferred to these two partial fractions, you can also put them together. So what do I mean by put them together? So you can also write this as over s squared right away, and because this is to the power of 2, so we know that you will end up with as plus b. So you have two choices. So either you're going to make them into two fractions like this, or you can also make it into one fraction and put them together, and at the top it goes as being as plus b. So either way is correct, and either way is going to give you exactly the same answer. But like from my past experience, I noticed that like reducing them to two fractions like this is going to be much easier actually. Like, yeah, it's going to be like more terms in there, but however, when you start substituting and do your calculation, it's going to be much easier for like with having two fractions. But it's totally up to you, so which one that you're more comfortable with. But let me warn you, so this is only for when you have s by itself raised to the power of n. So it cannot be when s plus a constant to the power of n. No, it's only when s is to the power s plus 0 raised some to the power of n. Okay, so that will be the special case.